So in this first section for Chapter 9, we are now going to learn how we can test a claim that people make based upon data and information that we can gather. So this section is just basically going to go through an introduction to what all this means. And then, like in the last couple sections, the last two sections, or chapters, the last two sections will actually have us doing the work. So, confidence intervals, which we just got done working with, are one of the two most common types of statistical inference. Use a confidence interval when your goal is to estimate a population parameter. So if we want to estimate the mean, the standard deviation, whatever, the proportion, the percent, we create a confidence interval if we want to estimate that value. The second common type of inference is called a significance test. It has a different goal. It's to assess the evidence provided by data about some claim concerning a population. So a significance test is a formal procedure for comparing observed data with a claim, also called a hypothesis, whose truth we want to assess. The claim is a statement about a parameter, like the population proportion P or the population mean mu. We express the result of a significant test in terms of a probability that measures how well the data and the claim agree. So in this example, which we're not going to do, you can open this applet if you'd like to, but it says a basketball player claims to make 80% of the free throws that he attempts. We think he might be exaggerating. To test this claim, we'll ask him to shoot some free throws virtually on an applet. So we're going to, what they're doing is they're setting the applet to take 25 shots, click shoot, and record how many of the 25 shots the player makes. Click shoot again for 25 more shots, and repeat until you're convinced either that the player makes less than 80% of his shots or that the player's claim is true. So a significance test starts with a careful statement of the claims we want to compare. The claim we weigh evidence against in a statistical test is called the null hypothesis, H sub 0. Often the null hypothesis is a statement of no difference. The claim about the population we are trying to find evidence for is the alternative hypothesis. So, in our free throw shooter example, our hypotheses would be the null hypothesis is that the proportion is equal to 80%, 0.8. That's the statement, the claim that we're trying to test. H sub A, the alternative hypothesis, is what we're trying to find evidence for. So we don't think that his proportion is 80%. We think it might be less. So our alternative hypothesis is that the proportion is actually less than 0.8. In any significant test, the null hypothesis is always the parameter value, P, mu, median, whatever, equal to the value. The alternative hypothesis is always either less than, greater than, or less or not equal to. So the alternative hypothesis, you have to read the problem carefully and ask yourself, are we saying that the proportion was too low, too high? What are we looking for? Or do we just think that the proportion is not what they're claiming? The alternative hypothesis is one-sided if it states that a parameter is larger than the null hypothesis value, or if it states that the parameter is a smaller than value. It's two-sided if it states that the parameter is different from the null hypothesis. If I claim I don't think Johnny shoots 80% free throws, then our null hypothesis would be P is not equal, or alternative hypothesis, sorry, would be P is not equal to 0.8. We just think it's something different. So the hypotheses should express the hopes or suspicions we have before we see the data. It is cheating to look at the data first and then frame hypotheses to fit what the data show. Hypotheses always refer to a population, not a sample. Be sure to state H sub 0 and H sub A in terms of population parameters. Don't ever use p hat or x bar. That's the third bullet. It is never correct to write a hypothesis about a sample statistic like p hat or x bar. So suppose a basketball player claimed to be an 80% free throw shooter. To test this claim, we have him attempt 50 free throws. He makes 32 of them. His sample proportion of made shots is 0.64. What can we conclude about the claim based on this sample data? We can use software to simulate 400 sets of 50 shots, assuming that the player really is an 80% shooter. You can say how strong the evidence against the player's claim is by giving the probability that he would make as few as 32 out of 50 free throws if he really makes 80% in the long run. So if you look, our p hat was 0.64. In 400 different sets of 50 shots, there were only 3 times when the shooter made as few as 64%. Based on this simulation, our estimate of this probability is 3 out of 400. 3 times out of 400, he shot less than 64%. That's 0.0075. The observed statistic is so unlikely if the actual parameter value is p is equal to 0.8 that it gives convincing evidence that the player's claim is not true. There are 2 possible explanations for the fact that he made only 64% of his free throws. 1, the null hypothesis is correct. The player's claim is 0.8, but just by chance, a very unlikely outcome occurred. 2, the alternative hypothesis is correct. The population proportion is actually less than 0.8, so the sample result is not an unlikely outcome. So here's the basics. Here's what this boils down to. An outcome that would rarely happen if the null hypothesis were true is good evidence that the null hypothesis is not true. So this leads us to p-values. The null hypothesis, h sub 0, states the claim that we are seeking evidence against. The probability that measures the strength of the evidence against the null hypothesis is called a p-value. The probability computed assuming h sub 0 is true, that the statistic would take a value as extreme as or more than extreme than the one actual value, is called a p-value of the test. Small p-values are evidence against h sub 0 because they say that the observed result is unlikely to occur when h sub 0 is true. Large p-values fail to give convincing evidence against h sub 0 because they say that the observed result is likely to occur by chance when h sub 0 is true. So a p-value is kind of like a probability, right? You get that? So the final step in performing a significant test is to draw a conclusion about the competing claims you were testing. We make one of 2 decisions based on the strength of the evidence against the null hypothesis. We either reject the null hypothesis or you fail to reject the null hypothesis. It has to be one of those 2. You cannot accept the h sub 0. You can never say that. So a fail to reject h sub 0 decision in a significance test doesn't mean that h sub 0 is true. For that reason, you should never accept h sub 0 or use language implying that you believe h sub 0 is true. So in a nutshell, our conclusions to significance testing comes down to this. When the p-value is small, we reject h sub 0. That gives us convincing evidence for h sub a. When the p-value is large, we fail to reject h sub 0, and there's not convincing evidence for h sub a. There's no rule for how small a p-value we should require in order to reject h sub 0, but we can compare the p-value with a fixed value that we regard as decisive. It's called the significance level. We write it as alpha, the Greek letter alpha. I see it's not showing up here. Looks like that. If the p-value is smaller than alpha, we say that the data are statistically significant at level alpha. In that case, we reject the null hypothesis and conclude that there's convincing evidence in favor of the alternative hypothesis. When we use a fixed level of significance to draw a conclusion in a significance test, if the p-value is less than alpha, we reject H sub 0. If the p-value is greater than or equal to alpha, we fail to reject H sub 0. Okay, I know that's kind of confusing. I need you to make sure you watch the examples, and I'll try to tie this all together. Again, these are the sections I think you end up hating because we're not doing the work. You're not actually seeing how this all plays out.